This is Climate Watch. I'm Zhao Ying. Welcome to the show. Asian countries are experiencing an exceptionally active typhoon season. So far this year, 20 storms have formed in the Northwest Pacific and the South China Sea, well above the historical average. Some powerful storms have brought torrential rainfall far inland, causing severe flooding across parts of China. Typhoons and hurricanes are among the most destructive natural disasters on Earth. Every year, they affect roughly 1 billion people around the world and cause enormous economic losses. With satellites and supercomputers, we've become quite good at predicting the general path of a typhoon. But predicting its intensity remains a major challenge. Sometimes a relatively weak storm can undergo rapid intensification in a matter of hours, leaving communities in its path with very little time to evacuate. Now, a new study published in Communications, Earth and Environment suggests we may be getting closer to a breakthrough in intensity forecasting. A team led by our guest today has found that existing forecasting models have not fully captured the role of ocean waves in the complex interaction between the ocean and the atmosphere. The team has developed a third-generation typhoon forecasting model that better represents these processes. In the Northwest Pacific, the new model increased the probability of detecting rapid intensification to 90%, compared with 10 to 50% for existing models. Joining us today to unpack these findings is Professor Qiao Fangli. He is a member of Academia Europaea and a professor at the First Institute of Oceanography under China's Ministry of Natural Resources. Professor Qiao, it's great to have you with us.
Thank you.
So, with today's satellites, supercomputers, and sophisticated weather models, why are typhoons still so difficult to predict?
Typhoons are among the most complex weather systems on Earth. While satellites and advanced models have greatly improved our understanding of their environment, many challenges remain. A typhoon involves interaction across many different kinds of scales, from large-scale atmospheric circulation to storm-scale convection, and the turbulence-scale ice interactions. Some of these processes occur at very small scale and are quite difficult to observe, which makes them challenging to represent accurately in models. Typhoon forecast is based on numerical model, and the model performance really on turbulence understanding. Unfortunately, as Nobel Prize winner Rita Feynman pointed out, turbulence is the most important unsolved problem of classical physics. So in general, our understanding on turbulence is quite shallow, which is the main obstacle for accurate typhoon forecasting.
I learned that we have actually become much better at predicting the path of a typhoon, but predicting its intensity or how strong it will become is still a challenge, right? Why is that?
We have made great progress in predicting typhoon tracks because they are largely controlled by large-scale atmospheric circulation that can be relatively well observed and forecasted by current models. However, predicting typhoon intensity remains challenging because it depends much on complex ice interaction and small-scale processes inside the typhoon. As we know, typhoon is generated on the ocean, and its intensity really on how much energy it can take from the ocean. This is called the ice flux. Unfortunately, our understanding on ice flux is not advanced. For example, how much heat and energy a typhoon receives from the ocean, how the upper ocean responds to strong winds, and how these challenges feed back to the typhoon are all influences strengths. These processes are still difficult to observe and represent accurately in current forecasting models. So this is the reason why we could not accurately forecast the typhoon intensity.
So rapid intensification can turn a relatively weak storm into a very dangerous one in a very short period of time. But why is it so difficult to predict when that will happen?
We can regard a typhoon as a heat engine. A typhoon strengthens rapidly when it gains much more energy from the ocean than it loses through processes such as friction. However, accurately representing these energy exchanges remains challenging, particularly because the role of ocean surface wave in ice interaction has not been fully understood and represented in traditional type models. Improving our ability to better express this process is vital because rapid intensification can leave communities with very limited time to prepare.
Yes, and we often hear that warm ocean water fuels typhoons, but your research actually suggests there's more to the story. So, can you tell us more on what role ocean waves can play and how a typhoon develops and intensifies?
Warm ocean waters is indeed an important energy source for typhoons evolution, but the ocean surface is not simply a passive fuel tank. The ocean surface is constantly changing, and the ocean waves plays an active role in the interaction between the ocean and the atmosphere. Strong wind from a typhoon generate high surface waves, and these waves then affect the momentum, heat, and moisture exchange between the ocean and the atmosphere. These changes can directly influence the typhoon's intensity. For example, breaking waves can generate sea spray. We can say that phenomena along coastal areas and strong wind, very like foggy weather. So that greatly enhances the heat and moisture transfer from the ocean into the atmosphere. That means more heat will be transferred to the atmosphere. At the same time, surface wave and sea spray can also change the roughness of the ocean surface, which influence how energy is transferred between ocean and the storm. And the strong wind, the effect of the sea spray, like the effect of oil, making the wind on a slippery ocean surface, so the wind will become stronger. Surface waves can greatly enhance mixing in the upper ocean, and this mixing can cool the sea surface temperature. As a result, the heat transfer from ocean to atmosphere will be reduced. This third process is crucially important to imbalance the first and second processes. So these three processes create a feedback loop. The typhoon changes the ocean, and the ocean in turn influences how the typhoon develops and intensifies.
Yeah, so actually the wave can change the way a typhoon interacts with the ocean. So does this mean the typhoon is, in a sense, creating conditions that then affect its own development?
Yes, in a sense, a typhoon should not be reviewed as a system that simply responds to pre-existing ocean conditions. It actively changes the ocean through its strong wind. The interaction between ocean and the atmosphere is a key to understand a typhoon. As the typhoon moves across the ocean, it generates strong surface waves and drive exchange of heat, moisture, and momentum between the ocean and the atmosphere. This can then feed back into the typhoon's evolution. So, rather than developing over a fixed ocean surface, the typhoon is interacting with the ocean as a fully coupled system.
Yeah, and can you tell us more about your third generation typhoon forecasting model and what makes it different from the models that came before it?
The key innovation of the third generation typhoon forecasting model is that it fully incorporates three ocean surface wave processes into the coupled model. During the past 70 years, two generation typhoon models have been developed till now. The first generation typhoon model is only atmosphere models. These models over-forecasted weak typhoons and under-forecast strong typhoons. The second generation typhoon models are ocean-atmosphere coupled models, but the role of ocean surface wave at the ice interface was not represented. As a result, the second generation typhoon model are much better for weak typhoon forecasting. Unfortunately, these models are even worse in forecasting strong typhoons. In the world, our model is the first try to fully include three wave-related processes, which allow us to much better capture the physical process. In fact, the importance of surface wave feedbacks in typhoon forecasting is recently recognized by some leading international forecasting centers, such as the ECMWF in Europe, which has incorporated wave-induced drag feedback into its weather forecasting systems. Our model goes a step further by also incorporating both sea spray and wave-induced mixing effects, allowing us to more fully represent the role of wave in icy interactions.
Yeah, and also your tests suggest that this new model can predict the maximum intensity of rapidly intensifying typhoons much more accurately. Can you tell us more about that improvement? What does that mean in practical terms?
In practical terms, it means that forecasting agencies can have a more accurate estimation on how strong a rapidly intensified typhoon may become. This is particularly important because a typhoon can evolve into a strong typhoon very quickly, leaving little time for preparation. Improved forecasting can help authorities make better decisions, including when to issue warnings, how to prepare emergency response, and how to protect communities and infrastructures. Ultimately, the goal of improving forecasting is not only to improve scientific accurately, but also to help society become more resilient to extreme weather events.
Yes, but how much earlier could this approach tell us that a typhoon is about to rapidly intensify, and how much difference could that make for communities in the storm's path?
Our systematic model evaluation over 2023 and 2024 shows that this third generation model can successfully capture around 90% of rapid intensification occurring within the following 3 days. While the existing operational typhoon forecasting systems can capture only 20 to 50%. And the model also saw good skill in forecasting a typhoon's peak intensity. For example, during Super Typhoon Baiwei this year, our operational forecasting accurately predicted its maximum wind speed, with only a very small difference compared with observation. Research has shown that typhoon-related economic loss approximately scale with the square of forecasting intensity errors. For example, reducing an intensity forecasting error from 10 meters per second to 9 meters per second, only 1 meter per second. This would reduce the corresponding economic loss by about 20%. This illustrated how even a small improvement in intensity forecast can make a meaningful difference for disaster prevention and mitigation.
Yes, and actually, this new model has already begun to be applied at operational forecasting centers in China. How is it being used today, and what would it take for this approach to become more widely adopted internationally?
This model has moved beyond the research stage and is now being used in operational forecasting centers in China, such as the South China Sea Marine Forecasting and Hazard Mitigation Center, and also the East China Sea Forecasting and Hazard Mitigation Center. These forecastings provide valuable information for early warning and disaster prevention and mitigation. For wider international adoption, continued evaluation across different regions and forecasting systems is important. Collaborations with international forecasting centers will also play a key role. We believe that as the benefits of representing surface wave effects and ice interaction became clear, this approach can contribute to the next generation of operational typhoon forecasting worldwide and help communicate around the world, prepare for future typhoons.
So your research focuses on the Northwest Pacific. Why is better intensity forecasting particularly important for this region?
The Northwest Pacific is one of the most active typhoon regions in the world, and many of these typhoons eventually affect densely populated coastal areas in East and Southeast Asia areas, where several hundreds millions of people and critical infrastructures are exposed to typhoon risks. For these communities, knowing not only where a typhoon will go, but also how strong it will become is extremely important. More accurate intensity forecast can provide early and more reliable information for emergency response, helping authorities and communities reduce risks and better protect lives and properties.
Yes, and we know that we are potentially heading into a particularly strong El Nino event this year. How could a very strong El Nino affect typhoon activity in the Northwest Pacific?
A strong El Nino can influence typhoon activity in the Northwest Pacific by changing ocean conditions and large-scale atmosphere circulations. It can affect where typhoons fall, how they move, and whether environmental conditions become more favorable for intensification. However, the accurate intensity of an individual storm depends on factors such as wind shear, atmosphere moisture, and ice interaction. Therefore, El Nino can provide important background conditions, but it influences the fate of every individual storm through background ocean and atmosphere conditions.
And as climate change continues to drive sea surface temperatures higher, how is that changing the game for typhoon forecasting?
Climate change is creating new challenge for typhoon forecasting because it is changing the ocean and atmospheric environments in which typhoons develop. For example, warmer ocean will provide more energy for typhoons, potentially allowing typhoons to become stronger and intensified more rapidly. This means that forecasting models need to accurately represent not only the typhoon itself, but also the ocean and atmosphere background environment. Climate change will also change the ice interaction that control how the typhoon gains and loses energy. This is also why improving the representation of an ocean surface wave process is becoming increasingly important. As the ocean environment changes, we need models that can realistically capture the two-way interaction between the atmosphere, ocean, and surface wave to forecast how individual typhoons will evolve.
Yeah, and it feels like some storms in recent years are not just getting stronger, but they also move slower and stalling over cities. They dump massive rain for days. Is ocean surface behavior part of why these storms stall or take erratic routes?
The ocean can directly influence some aspects of a typhoon, but maybe not the direct factor controlling whether a typhoon stalls or takes an erratic path. Typhoon movement is primarily controlled by large-scale atmospheric circulations, such as steering flow and the subtropical high. Of course, oceans have much influence on atmosphere circulations. The ocean is a major source of moisture for typhoon and therefore play an important role in their rainfall. For example, when ocean surface waves break, they generate sea spray that can transfer additional moisture from the ocean into the atmosphere. This moisture can then contribute to the intense rainfall produced by typhoons. So, while large-scale atmospheric circulation remains the main factor controlling a typhoon's movement, ocean and surface wave process are important for understanding how much rain a storm can produce. Our research suggests that considering surface wave in a typhoon model can greatly improve the forecasting ability on rainfall.
Yeah, and we know that nowadays AI is developing rapidly in weather forecasting. So can AI also improve typhoon forecasting as well? And what could it add to physics-based models?
AI has high potential to bring new capabilities to typhoon forecasting. It can learn complex and highly nonlinear relationships from large amount of historical observations and model data, which may help us identify patterns associated with rapid intensification and correct systematic bias in physical-based models. We believe that AI and physical-based models should work together. AI is powerful because it can learn from data, but the quality and completeness of typhoon data are quite limited. Our third generation typhoon model can complement observations by providing physical consistent and detailed information on typhoon evolution. AI can then learn from new model data, helping identify and correct bias in physical-based models. In this way, the two approaches can complement each other. Physical-based models provide the physical framework, while AI can learn complex nonlinear relationships from data and help improve the model's performance. The future of typhoon forecasting will likely come from combined physical-based models, advanced observation, and artificial intelligence. It should be mentioned that AI with low-quality model data and quite limited observation data may be not enough for accurate typhoon forecasting. We should pay more attention on physical process research. Finally, as was convincingly highlighted in the recent article by Smith and Soap published this year, they mentioned machine learning statistical estimation neither can nor should be expected to supplement physical-based simulation for weather forecasting.
Okay, but I mean, how accurate can a typhoon forecast realistically become? Like, is there a limit to how precisely we can predict a typhoon?
This depends on the model performance. So there is no limitation for the performance. With our improved understanding on the physical process, the model will become better and better, and we can get more accurate forecasting results.
And that wraps up this edition of Climate Watch. You can find more episodes on your favorite podcast platforms. Just search for Climate Watch and hit subscribe. Don't forget to leave us a quick review or share it with a friend. You can also email us at radio@cjtn.com with your questions or feedback. And stay updated on the latest climate stories with our Substack newsletter, Climate Choices. I'm Zhao Ying. Thank you so much for listening. See you next time.